doubt you have is already answered. And then we can go one by one in answering questions. So, okay. We're going to answer those questions based on the lecture this week. And I believe the lecture was really, really good. She was very easy to understand, Francisca. She was very clear on what she explained. So I believe we're not going to have any problems, and I'm going to be referencing her lecture. Okay. So the first question is, what does big O notation represent? And let's go through the options we have here. It says it's a measure of the complexity of an algorithm at large values of n. The other alternative says it's the runtime for an algorithm. And C says the difference in runtime of an algorithm between small and large values of n. And now we need to remember the lecture. In the lecture, she refers to n as the number of steps, because for big O, big O is a fair way to compare the performance of algorithms. And she was very clear that if you want to compare, you cannot go through runtime, because runtime depends on so many other factors. So the let's say the more fair way, the fairest way to go to compare things is if you find something that's common ground to be compared. And the number of steps an algorithm takes that's given by n, it's a fair measure for comparison. So if you admit that n is the number of steps, the big O becomes the number, the way to measure the complexity of an algorithm by the number of steps. If you call the number of steps n, we have our answer that you guys might know it now at this moment, that is letter A. It's the measure of the complexity of an algorithm at large values. And we take the worst possible scenario, because it's how we define the big O. We're going to take the worst scenario because maybe if you take the easiest scenario, you're not going to be fair. Maybe you're going to have, like, if you take just one single scenario and the simplest one, maybe you're going to find two algorithms that perform the same, but that's not the correct comparison. You need to take the worst scenario, then you compare the worst case that can happen, then you can compare. So it's defined as the worst scenario, so you can compare. In the worst case things happen, then you're gonna be doing a very fair comparison. Okay, question 2. Which of the following big O notations represents the algorithm with the lowest complexity? And if we remember the lecture again, I'm gonna try to open the lecture here. Let me see if I have it open here. There's a graph that's very, very useful. Yeah. This graph here. Let me see if I can make it larger. Yeah. So need to minimize the reposition it. Yeah, if I maximize it without repositioning. Good. So yeah, this graph, it's in the lecture. If you guys can't see here, you guys can open the lecture because it's on Canvas. You can see it easily there. But we see here a comparison of the big O's. and how it performs according to the number of steps an algorithm takes. The biggest one is a factorial. Then it comes followed by an exponential, a quadratic, a linear, square root, logarithm, and constant. And the big goes from right, the bigger is on the right, and then to the smaller to the left, whereas constant is the less big, or the smallest number of steps, the smallest big O. So it's clear from the graph, we can see how many steps we take and the size, the number of attempts and the size of n. And then we see clearly that the constant is the smallest one. The constant is here. It's this purple thing here. And the biggest one is the factorial. It's the gray thing that grows like insane here. Okay. So going back to the homework. Let's open the homework again. My internet is not collaborating. Yeah. So going back to the homework here, to the question. Which of the following big O notations represents the algorithm with the lowest complexity? And we saw that the constant one is the lowest complexity, and then this one would be bigger than this one together with this one, because 2n and n are the same, and then the power n power 2. So On and O2n are basically the same, because if you take this function to infinite, it doesn't matter anymore if you have a factor 2 multiplying. Francisco in the lecture says all the time, if you take this to 1 trillion, it doesn't matter anymore. So 2n and n are basically the same, and it's easy to realize that n squared is much bigger, n squared 2. Sorry, n to the power of 2. I'm sorry, it's fading in my language. It's much bigger than the constant function. So answer is letter B, O constant, O 100.
I didn't understand question 1.
Okay.
Can you please explain it again?
Yeah, I can. Okay. Big O notation represents, okay, to compare the performance of the algorithms, you need to find a far item of comparison, like a fair quality to compare. You need to find a common ground to compare. If you try to use, for example, the runtime doesn't qualify an algorithm. It can be, it's dependent, for example, on the performance of the machine. It can be dependent on like, even if the computer is overheating or things like that. But big O is about the number of steps you take to achieve a result. And we are defining the number of steps by n. That's how it was defined in the lecture, and the homework asks to reply based on the lecture. So if you use n to call the number of steps n, the thing you're going to be comparing is the number of steps an algorithm takes to perform a function. So it gives us the answer already. It's letter A. Big O notation represents the measure of complexity of an algorithm at larger values of n. And large values, because we take the worst possible scenario, and the worst possible scenario is the highest value. You need to compare the worst thing, because then you're comparing each in a fair ground. If you try to compare the simple scenario, you might be led to a mistake. So if you compare to the biggest, worst possible scenario, then you're going to be doing a fair comparison. So it's letter A. Okay.
Thank you.
Welcome. So question 3. Which of the following big O notations represents the algorithm with the highest complexity? We just saw the lowest. And when I was answering this question, I said which one was the highest. So I guess you guys know. It's letter C. It's letter C. So yeah, A and D are the same, because if you take this function to infinite, if n is equal to infinite, it's going to be the same thing. It doesn't matter if it's 2 trillions or 1 trillion, it's already big enough. And infinite, so twice infinite, it doesn't matter. So the highest complexity is going to be n2, because if you take a trillion, for example, and take it to the power of 2, it's going to be much bigger than a trillion. So letter C is much bigger. Okay. Question 4, and we need to pay attention. Question 4, what exactly it's asking? Question 4, let's read it first. Below are the complexities of a classical algorithm and a quantum algorithm for the same task. In which of the cases would the quantum algorithm be faster than the classical one? Note that this is referred to as quantum advantage. Now, if you read the question, you understand that this question is not affirming that quantum algorithms are better. It's not affirming that. It's just saying that, number one, this is comparing two algorithms, and number two, if the quantum performs better, this is called quantum advantage. It's not affirming that there's always a quantum advantage. So it's putting some scenarios, and we need to check in which one the quantum performs better. And the way we're going to compare is by comparing the big O's of both. And the one with the smallest big O is going to achieve a better performance. It's going to be considered the algorithm with a better performance, because it's going to use less number of steps to achieve a result, and this is going to perform better. So let's see case by case. The classical has a big O like this, O2n, and the quantum has O4n. And as we saw in questions 2 and 3, we saw that 2n and 4n, 3n, 10n, even 100n is the same as saying n. It's the same thing, because when you take this function to infinite, it doesn't matter this small factor multiplying. Option B, say, compares the classical n squared plus 100 and quantum n squared. And I would say this, I can affirm these are the same performance. One is not better than the other one, because when you take n to infinite, it doesn't matter if you have plus 100 steps. It doesn't matter. It doesn't take more time. It doesn't make a better or worse work, because it doesn't matter. When you take the number of steps to a trillion, to infinite, it doesn't matter if you add plus 100, if you plus 100 it. So they're the same. Let it be to perform the same. Now, question C compares n squared for the classical to the quantum O2n, and O2n plus 1,000 is the same as ON, and this is linear, while the ON square is like a parable. And yeah, we see clearly that letter C here shows a much, much bigger big O than this one. This function grows much, much faster. It means the big O is much more, it's much bigger. So it's letter C. This is when a quantum algorithm can perform better from the options we have here, okay? In this case, it doesn't matter. Both are going to perform the same. And in this case, it doesn't matter because both are going to perform the same. Question number 5. Which of the following quantum algorithm does not use an oracle?
I have a query on question 4, please.
Yeah?
On the option C, when we have O big O n square and O2n, so
Mm-hmm.
basically it will evaluate to n square and On, correct?
Mm-hmm. Yeah.
Now On is much smaller compared to On square.
Yeah.
So if we go to the lecture lab, if we see the table where we had that graph, which you just now showed us,
Mm-hmm.
between On and n square, so
Yeah.
n square is much more faster, correct?
Now, okay. You cannot confuse big O and like how fast a computer is, because big O is not about how fast the computer performs. It's about the number of steps. I said that the function grows faster. It means this function is bigger. It means big O here is bigger. And we say it's less, it's more efficient when the big O is smaller. So in this case, O to n is a function that grows lower than n squared. So in this sense, the big O is smaller. And if big O is smaller, the algorithm is more efficient.
Okay, okay. Thanks,
Okay,
thanks.
welcome. Yeah, when I said it aloud this morning, when I was explaining to my student, I realized that this could be subject of confusion. So to not forget, it means this, the function grows faster. It doesn't mean the computer performs faster, because big O is not about performing faster. It's about the number of steps, okay? To not confuse both concepts. And if
Thanks.
I say it, okay, welcome. If I say it wrong, you guys can interrupt me and say, hey, but you said, okay? Because it's a confusing concept. So, which the following quantum algorithm does not use an oracle? And unless you guys read about it or paid very, very high attention to the lecture, there's no way to know, because you need to know the algorithms to know which one does not use it. I know some of you didn't have your labs yet. So in the lab, the instructor is going to talk about the DJ algorithm. Okay, it's this first one. And this one, this one, yes, it uses an oracle. Okay, it's gonna be taught in the lab tomorrow. And for those who already did the lab, we know that this algorithm uses an oracle. And the Grover search, that's gonna be we're gonna hear about it next week. The lab next week is gonna talk about the Grover search. And this one also uses an oracle, okay? The one that doesn't use an oracle is Shor's algorithm, this one. Okay, Shor's algorithm doesn't use an oracle. Okay, but the only way to know is either paying attention to the lecture and to the lab, or to the labs, or even like searching it, reading about it in the web, in the material, the course material, all the extra readings we have there. Yeah, so the only one that doesn't use it is the Shor's algorithm, okay? Question 6, it's only gonna be obvious. It's a silly question. It's not silly, but it's gonna be obvious for those who do the lab. Do you want to remember the lab? And tomorrow when you guys do the lab, the ones who didn't do the labs yet. But like, which of these combinations of gates could be used to make a balanced 2-qubit oracle? But the question says which of these combinations of gates, and the only option we have with a combination is this one. So it's very obvious that's letter C. But apart from being obvious in the exercise itself and the question itself, you guys are gonna see tomorrow. It's a very interesting subject. In the DJ, the Deutsch-Jozef algorithm, people came with a super smart way to see if a function returns balanced replies or constant ones, if the function, sorry, must rephrase that. If a function is balanced or if a function is constant. And it needs to be clear that this algorithm was made to prove for the first time with a very specific problem to compare a classical and a quantum performance, quantum and a classical algorithm, to show that in one you need 2 steps, and the other one you take only one. You're gonna see this in the lab. If you take more qubits, it's 2 elevated to n. And the classical, it's gonna be only 1 step for quantum. And this is because quantum has the property of superposition and interference. And then these people in 1998, if I'm not mistaken, if 1992 or 1998, I'm not 100% sure now, they came with this idea. They were smart enough to realize that they could, with only 1 step in this specific problem, to show that a function was balanced or constant. It's not a proof for general quantum computation, but was the first time with a very specific oracle, people could prove that a quantum computer can have a better performance, in the sense that it can have a smaller big O than a classical one, okay? So you guys pay super attention to the lab. If you didn't understand very well, you go to the recordings and watch it again and try to do by yourselves. But it's a very specific situation where this was proven, okay? It's very interesting, and yeah, it can be confusing, but it's possible to understand, okay? After you understand it, you understand as it should be understood, as what it is, it's gonna be clear, I promise. And the last question, which quantum algorithm provided the first theoretical demonstration of quantum advantage? I just said, at this point, you guys might know. It's letter A. It's the lab of this week, the lab some of you are gonna do tomorrow. It's the Dodge-Joseph algorithm, was the first theoretical demonstration. And this morning, a student asked me how these guys came, like they had a quantum computer, they kept trying. No, they had a brain and paper and a pen, and they tried, they did all the calculations, and they knew that there are these possibilities in quantum, and they knew that was possible. They knew it was like they could do it, so they kept trying, and by trial and doing the calculations, they got to this algorithm. It's very smart. It's how science sometimes work. Sometimes scientists have the problem and they have the solution they want to achieve, and they need to find the in-between. And as I told my student this morning, sometimes this in-between is so good, that's not applicable to that problem they were looking. You can apply to other problems, and it happens all the time. So science is just like that. It's a lots of work and a little bit of luck. There's these ingredients to do good science. So yeah, I'm open to questions now if you guys have specific questions. And then if you guys don't have questions, I can go through the homework again. So I'm going to open for questions.
Can I ask you a question, ma'am?
You want to see question 1?
No, can I ask you a question?
Oh, yeah, of course.
Okay. Ma'am, believe me, fall of 2019 and spring of 2020, I struggled a lot learning these algorithms. I could never figure out what was the big deal about it. This is the first time you, the professor in the lecture, and my TA on Wednesday explained me the quantum advantage, the big O. Okay, and that made me realize why there's an advantage. Otherwise, I've never understood why there's a quantum advantage. Okay, I had no idea. Now, the question I have for you is 2. Number 1, I think in question number 3, you are comparing those 3. Can you just go to question number 3? No, question number 4. Yeah, question number 4. Yeah. So is it not true that for every problem, there'll be a quantum advantage because the big O is always smaller for a quantum computer compared to a classical computer. Is that a good conclusion or no?
No, it's not
Why?
all. It's not
Why?
all. Why? I can't remember now on the top of my mind. I can't remember, but there are some problems. I read about it. I had this example some weeks ago. I forgot.
That's
But
okay. That's okay. Ma'am.
sorry, what?
That's okay, ma'am. If you ever, when you get the reference, just share it with us. Okay.
Yeah, but it's not conclusive. Sometimes quantum has proven not to be better so far. And I keep saying this is a large new field. You have so much to find about it. Quantum computer is very new. And there are some ways we can go. Either it's gonna be a revolution and quantum is gonna prove to be better than anything. Either we are awfully wrong, it's gonna be worse, it's gonna be a waste of time that I particularly do not believe. Either the best way is gonna be a hybrid solution, classical plus quantum. The fact is there's still a lot to study because quantum is new, is a relatively new field of research. It's from the beginning of the 20th century, and if you compare to the rest of sciences, it's so new. Only in quantum computing, quantum information, there's like quantum noise, quantum materials, quantum problems. There are theoretical problems, there are mathematical problems that we didn't find still. There is mathematics inside this that you have no idea. There's mathematics. I have a PhD in physics, and I'm telling you, there's mathematics I went to find about like last year. I have had no idea how to do. So there's so much to learn and to explore. And any of you that's studying this now will have a chance, if you want to go to pursue this career, you guys are gonna have a chance to make your contribution for sure. It's a huge field. So it's not true that quantum advantage is always happening at the moment. No, for some problems, quantum computers have not performed very well yet. The calculator, I remember now it was a problem like making a calculation, and like the calculator, no, phone does better than the quantum calculator. It was a problem like that. But if you search, you can find it easily.
Okay.
It's not true that
One more question, ma'am. When I was studying these algorithms last year, there's no way in any of the articles on Google they mention about the big O. Where can I find a little more detailed information about the big O for the Deutsche algorithm, Shor's algorithm, and Graeber search algorithm? I could not find about the big O. They talk about all the mathematics of the world, but nothing about the big O and why it is better.
Did you do the lab this week already, or is
No,
gonna
I
be?
didn't do it. I'm sorry. I did not.
Okay, no, it's not a problem. I'm not challenging you or anything. I'm just saying tomorrow in your lab, you're gonna see why the instructor is gonna explain. You're gonna see better tomorrow. I can say it now, but it's by analyzing both algorithms. When you look at them and you see how you do steps for the classical and how you do the steps for the quantum, by simple analysis, you can realize it for the Deutsch algorithm. For the Grover algorithm, the lab's gonna be next week, and you're gonna see that there too. So for each problem, you have different ways to approach.
Okay.
Tomorrow you're gonna see it, and if the person doesn't explain very clearly, you can ask the instructor. We'll have no problems explaining to you again. But in the recording of the lab that is already in Canvas, and during the lab 4 I did this week, it was explained.
Okay. Thank you
Okay.
very much for the very clear and for educating all three of you, and including president of this coding organization. Okay. Thank you very much.
Thank you. I'm very glad when people say they're understanding, because sometimes I think I'm not clear at all. But I get happy.
Ma'am, may I ask a question?
Yeah, of course.
So I had write a program on Grover's search algorithm. So basically, I tried to replicate the coding in my notebook and I succeed. But I'm not sure why Grover search is working fine. So for example, when I try to search something out of an array of 10 elements, in classical computing, it takes, I mean, about 10, iterations. But in Grover search, it gives me a result in just one shot. But I'm not sure. I mean, behind the screen, what is happening? I'm not sure. I get my answer, but why Grover search fast? I mean, search is so fast out of that array. So can you
I
explain that?
will, I will give you a very rough explanation because the Grover is gonna be seen next week. So I'm just gonna,
Okay,
the only thing I can tell you it's because the probabilities in quantum mechanics, you work with probabilities. So you have one of the square root of n instead of n you would have in classical. So
correct.
your big O is not sorry, in classical it would be 2 elevated to n, 2 power n.
2
And,
power n, right?
yeah, and 1 over square root of n is much faster. So it's much smaller, sorry. It's a much smaller big O, sorry. And that's why it's because of quantum, the probabilities, because probability in quantum are 1 over square root of n.
Square root of n.
Yeah.
So that's I understood, but by logic, if I want to search something out of an array of 10 element, I see I am coming from software background. So when I want to search something, I will you see my program will verify each and every element. That is the normal procedure, right? But I am not sure how, I mean, this Grover search suddenly find the right element out of the 10 in just one shot without verifying the other elements. So, I'm not
I-
sure how it happens.
okay.
I mean, it's like, magic, magic or something like that.
Yeah, okay. It's the last thing I'm gonna say about the Grover because I don't want to confuse people. Grover is gonna be seen next week. But again,
Okay.
it's the quantum. I will have a poetic license here. Yes, it's the quantum magic. In quantum, in
Yeah,
quantum, all the states are there. The cat's dead and alive until it's not that the cat's dead or alive. The cat is
right.
dead and alive at the same time. When you open the box, you find you collapse the state. It's the same idea. It's the magic that quantum does. Okay, but I would ask you to be more patient because I don't want to confuse the students and I need to give them space to ask about this specific homework.
Fine, fine, fine.
And yeah,
Thank you.
I just don't want to put the car in front of the horses now to not confuse people. This week it's gonna cover Grover search and then yeah, everyone's so curious about it, but it's gonna be covered. Okay,
Yeah, thank you.
welcome. Any other questions about the homework? If there are no questions, I will go through the questions again because some people came late and they might have not seen the other
Uh,
answers.
can you explain the last question?
Yeah.
It's, I mean, which quantum algorithm provided the first
Which quantum algorithm
It's
provided?
DJ algorithm, I guess.
It was a Deutsch-Joseph algorithm, the
Yes,
first one
yes.
that showed the first theoretical demonstration of quantum advantage. And yeah, and they did by hand. They did like calculating. Maybe they used a computer just to help with some mathematics, but I'm not sure. It's theoretical. Yeah,
True.
the calculation by trying. And one of the hardest problems in quantum is finding a good oracle. Finding the
Hmm.
oracle is very hard. So it was the biggest challenge, was finding the oracle. For all the problems, finding a good oracle is the hardest problem. But the oracles for quantum, the ones I saw so far, are
Hmm.
all based on this quantum magic that you can superpose and interfere. states.
Hmm.
So that's
Mhm.
where the quantum magic happens. You're gonna have the influence of quantum bits on one another because of like simple things like Hadamard gates and CNOT gates. They
Hmm.
make so much. It's so simple and so complex at the same time.
True.
Okay,
Thank you.
welcome. Any other questions about this homework? Okay, so I'm gonna go through the questions again for the students that couldn't join earlier. I'm gonna explain all the questions again. And this time when I'm explaining, you guys can interrupt me, okay? Okay, so first question, what does big O notation represent? So we are replying these questions, answering these questions according to the lecture we saw on Sunday that's recorded on Canvas, okay? And on that lecture, we define N as the number of steps we go to perform an algorithm, for an algorithm to achieve a result. And the big O is the common ground you have to compare performance of an algorithm. Because if you go to speed of the machine, for example, even an overheat computer can act slower than a cooled one. So the big O provides a fair ground. I think that's possible to compare. If you're comparing fruit, you cannot compare oranges to bananas. You're going to compare oranges to oranges. You don't want to compare like, oh, but you get a banana and then you say, but this banana, this orange, I don't know, it's more acidic than this banana. Of course, the orange is an orange, the banana is a banana. But if you get two oranges, then you can compare in common grounds. Then you can say this orange makes a better orange juice. You cannot make an orange juice with a banana. So it's a common ground, a fair comparison. And we get the worst case scenario, the highest number of steps, because if you take in the very beginning, you can be misled. You can think that they perform equally or differently. So you take to the worst scenario possible, the highest number of steps, and then you compare and then you see. So it's letter A, okay, a measure of the complexity of an algorithm at large values. Question 2, which of the following big O notations represents the algorithm with the lowest complexity? So the lowest complexity is the lowest number of steps. And in this sense, 100 is a constant. It doesn't go crazy. This function doesn't go insane at the infinite. At the infinite, 100 is going to be 100. These grows too fast. So it's a very big number. And these are small. Big O's, they are the same. 2n and n are the same. So the lowest complexity is the constant one. It's letter B. Which of the following big O notations represents the algorithm with the highest complexity? I just said, for if the lowest is like the constant, the biggest complexity is the square, n square. So it's gonna be letter C. Okay, it's the function that grows faster. So it's the big. Now, question 4 is the question we were just talking about. And we're gonna read the question, say, and see exactly what it says. Below the complexities of classical algorithm and a quantum algorithm below are the complexities of a classical algorithm and a quantum algorithm for the same task. So we're comparing the same task in both cases, like classical and quantum are performing the same task. In which of the cases would the quantum algorithm be faster than the classical one? Note that this is referred to as quantum advantage. So the question is not affirming that there's always a quantum advantage. The question is asking in which case there's gonna be a quantum advantage. And as we know, when we compare O2n to O4n, there's no difference, because when you take this to infinite, 2n and 4n are going to just be behaving as n. So it doesn't make any difference if it's 2n or 4n. They're going to behave the same if you take this n to infinite. In the same sense, if you compare n squared plus 100 to n squared, you're going to perform the same, because it doesn't matter if you take this to infinite. Adding 100 makes zero difference. So they're performing the same. Now, when we go to a classical algorithm that performs in with a big O at n squared, in a quantum algorithm that's just the order of n, because 2n plus 1,000 is just the same as On, we see that the quantum algorithm here performs much better. So it's a smaller big O, and it performs better. So in this letter C, we have quantum advantage. A and B are performing just the same. C, there's a quantum advantage because B goes smaller, okay? Question 5. Which of the following quantum algorithm does not use an oracle? And as I said before, if you already did your lab, you're gonna know that Deutsch-Jozsa algorithm uses an oracle. And if you paid attention to the lecture, you're gonna remember that the Grover search also uses an oracle. But you could also have searched for this answer, because if it's not obvious, because we need to think that you guys don't know the algorithms yet. It's not supposed to know, like we shouldn't suppose you know. You guys can know and do your research, but like supposing, because in this course we didn't talk about the other algorithms yet. It's just if you paid attention to what the instructors said during the labs and the lecture, the only algorithm that doesn't use an oracle is Shor's algorithm. And the Grover search algorithm is gonna be talked about next week in the next lab. It's gonna be about Grover search. Okay, then we have room to ask many questions about the Grover search and all the quantum magic behind it. So question C, as I said before as well, it's kind of silly because it asks about a combination of gates. And if you know nothing about balanced functions and about algorithms or anything, it's asking combination, and the only question we have a combination, it's letter C. But like explaining why, in the lab, we saw about the DJ algorithm, and we saw that it uses X gates and C naught gates to build the oracle. And when it's balanced, we use X gate plus a C naught gate, making a combination. And yeah, if you saw the lab, you remember. If you didn't see it yet, you're gonna see tomorrow, because there's a lab tomorrow for the ones who didn't have the lab yet. So it's gonna be obvious. And the last question is, which quantum algorithm provided the first theoretical demonstration of quantum advantage? And it was the Deutsch-Jozsa algorithm, okay? You're gonna see in the lecture, in the lab tomorrow, the ones who did the lab saw it already. It was for the first time. People could come with a very clever way to with a determined input to see a determined output, and see, and by the output, say if it's balanced or a constant function that's inside the oracle. And it's very clever. It's a very specific example. It was for a very specific time to show that there's possible to have quantum advantage. And yeah, you guys, if you didn't understand better in the lab, I advise to see the recording again and to accompany it again, because yeah, it's not that complicated. At first it looks very weird and complicated, but watch it again and again. Don't give up. You're going to understand it. It's very interesting. And it's very amazing, like how quantum can do such a great thing. Okay. So any other questions?
Yes, ma'am. Can I ask you a question?
Yeah.
See, so the one advantage of quantum algorithms or quantum advantages in many situations is the big O. Second is teleportation and cybersecurity. What are the other advantages of quantum algorithms or quantum computers over classical computers which are missing out?
Okay. So if you're talking about quantum advantage, we're talking about the big O comparison. Okay.
Okay, okay.
So when you talk about cryptography, it is still about how much a classical computer would take to do such good keys or such clear, let me rephrase. The quantum key distribution is great because it's a way to get rid of spies. So in this sense, it's a clever way to distribute a key. Quantum teleportation is going to be maybe the way we're going to transfer information, but I wouldn't say at this moment it's a better thing, because the maximum we did so far was less than 1,000 miles quantum teleportation, while we know that classical can transport information from here to Mars, for example, or from here to the sun. So, and quantum teleportation we could only do for less than 1,000 miles. So, at this like if you ask me today, the answer is I don't know if it's gonna be easiest in the future. I truly don't know. I hope yes. I want a better world, yes, a better way of communication, yes, but I truly don't know. Either it's gonna be a huge mistake, waste of time, you're going to just learn more quantum physics, and maybe in the future you're going to apply for other things. Like, let me just fix this. Learning is never a waste. It's never a waste of time. But maybe we will find out that we were going to the wrong direction. Okay, let's put it like that. Maybe we realize, oh, we shouldn't have lost time doing this. We should like use all this knowledge for that. Or maybe we're gonna find, oh, perfect, we went all the way to the correct path. But the answer is we still don't know. It's all very new. One of the problems is to generate to build good single photon sources. It's still a problem. There are a lot of fields. There's quantum noise. There are quantum materials. We need to find materials that are superconductive, even at room temperature. It's one of the problems we have now, because the quantum computers at the moment need to be super cooled. They need liquid helium temperatures. It's nearly to absolute zero to work well. Sometimes you need, I might be saying it wrong because I don't have the experimental experience on that, okay? But I know they need to be super cold. Yeah, so there's so much we need to search and find still. So I can't affirm to it's gonna be the future. I hope, and I think it might be the future, but I can't affirm now. Okay, but that's my view. Okay,
Thank you, ma'am. Thank you very much.
you're welcome. Yeah, any other questions? So, yeah, if there are no other questions, I think I can wrap up, because, yeah, I don't think it was very hard week this week. I think the lecture was very, very clear. Unless you guys have any other doubts, I guess we can wrap it up.
It was quite easy this week.
Yeah, well, the thing is, I talked to my students this morning during the homework section. I think after having so much Qiskit, so much Python protocols, it was like mind blowing for you guys. So much quantum physics. And this week was like, okay, this is math. This I understand. It was like, oh, okay, now I understand it. So it was a bit easier. So, which is good. It's good to have a break sometimes.
I have one question.
Oh yeah, say.
Yeah, there are, various algorithms, and I mean, can you suggest some, good reference where we can really study all the algorithms together? Because, when I learn one algorithm, I mean, and when I try to learn another algorithm, I forgot. I used to forget the other algorithm which I already learned. So, I mean, it's very difficult to remember all the, algorithms. So, is it anything which we can refer?
I myself learned using the Qiskit textbooks.
Okay, yeah.
They are very well explained there. You can just do simple Google search for quantum algorithms. It's also another way. And the Wikipedia articles are not bad on this. They're really good.
Okay.
They have explanations. And then if you go, whenever my criteria when I go to Wikipedia, because anyone can edit it, I see if it has references. If it has references, then it's a good. And see, this one
Right.
is full of references. So whenever, see, whenever it says something, it has a reference that you can check. That's my criteria to say a Wikipedia article is good. So it's a good way to start if you go to the Wikipedia item. And whenever
Okay.
it talks about the subject, you go to the reference it says and try to read from there.
Right.
Okay.
Okay. Yeah.
Good way
Got
to
it.
start. Because I didn't learn it from books. I learned by doing it with the Qiskit textbook. Also, Amazon AWS has a thing called Bracket. It's
Yeah,
also
it's bracket.
you can read from there too. They have some explanations there, even for the algorithms. I saw them there. They are
Okay.
good explanations. They're a bit harder to find there in the documentation. You need to dig a bit more there in AWS, and they have their own library too. You can explore there too. It's a good way to
Yeah.
understood. If you can do in Qiskit and one more, it proves that you really understood it.
What is
Okay.
bracket, madam?
Bracket is the
Okay.
equivalent of Qiskit for AWS.
Physical
It's
kit for the
it's basically implementation of quantum by Amazon.
Yeah,
okay by Amazon. Okay, okay.
sorry, not Browlet, it's Bracket. Haha. It's this.
Okay.
Amazon Bracket.
Yeah, it's
That was fun.
BRAKET.
Yeah.
Thank
So
you, Devang.
my AWS is opening in Portuguese, but because my machines are in Brazil, but you can find it in English too. Okay. And yeah, basically you need to read articles about it.
Okay. Yeah. Thank you.
Welcome.
Where are you based, Devang?
Sorry, what?
No, I was just asking Devang. Where is he based? That's okay, ma'am. Don't worry.
Okay. So yeah, any other questions? If there are any, say.
Wish you a good weekend, ma'am. Both of you, all of you.
Oh yeah, have a nice weekend. So if there are no other questions left, I'm going to let Rachel go.
Thank you for a fantastic session once more. Bye.
Oh, thank you. Thank you. You guys have a wonderful weekend. Take care. Be safe during this crazy pandemic times. Okay.
Have a good weekend. Bye.
Bye. Thank you. Bye.
Thank you.
Thank you.
You too. Take care. Bye.
Yeah. Bye. Bye.